And hit, got it. Okay. Oh, so we are coming up to the final stretch end of the semester. So we're going to cover L'Hopital's rule today and Friday. On Friday, my course coordinator, Chris, is going to come observe me. So he's just here to take notes on my teaching, write down all the awesome things I do. Yeah. Oh, let me see when the final is. I put it on my personal calendar, so give me a sec. We might be. I think I had two of my finals end up on the Friday. Come on, Google, you can do it. So the week of the 2nd and the 4th, um, the 6th is study day, so there's no classes that Friday. And then finals start the week after that. So if I can just convince Google that it wants to do the thing. Yep, our final is at 11, so 11 to 12:50 on the Friday, the 13th. I'm also giving a final from 11 to 12:50 on the Monday. Um, so that room has some open seats. So if you wanted to take it early, I could probably work that out. I might even be able to work in some time on Tuesday or, well, Wednesday more than Tuesday. But just if you need to get out of here early, email me, we can figure it out. Because I know, like, especially with dorms and apartments, like having a final at the end can be a pain. Okay. So next week, we're going to have the review for exam 3 and then exam 3 itself. The practice problems should get posted and assigned, I would assume, by end of the day today. Like normally we have the old set, we modify it, we assign it. The old set went missing, so we're having to create it from scratch again, so it takes a little longer. Yes. All right, so exam 3 is going to be 4.1 through 4.8. So that is related rates, critical points, mean value theorem, first and second derivative test, optimization, and L'Hopital's rule. So we're going to have something from all of those. Most of them are actually pretty similar to what's in WebWork. I don't want to say all of them and then they're not. Mostly because I haven't looked at WebWork completely. All right. I published this like late Monday, I think. So I just went ahead and published the rest of the modules. All right, so the class notes for 4.8 are here. And then I've also uploaded this, writing assignment number 3. We put themes on all the problems, so it is very Thanksgiving or Christmas themed. Mostly Thanksgiving. So there are again 5 questions. And they're similar to, but a little more complicated than what's going to be on the test. But the ideas behind them are real good. And that is going to be due next Wednesday by 11:59, same day as the test. All right, Thanksgiving week. We do not get the full week off. Classes are still running Monday, Tuesday, and Wednesday. And we've got 2 new sections to cover that week. The Wednesday class will likely be on Zoom. I mean, I have Zoom open all the time. I'm not going to drive to campus on Wednesday because who the hell's going to be here? I'll still do office hours if anyone wants to pop in, but again, I will be highly shocked. But if you do, like, email me, let me know. That way I can make sure I'm on, because Zoom will log itself out after a while. If you need to attend online for the Monday and the Wednesday there, that's fine. No judgment. Like, some people get told by the parents you're babysitting your siblings and you're like, I have class. Or you get told we're going on vacation and you're coming. So hopefully that's not a shock to most of y'all. All right. Questions about any of that? Scheduling, rest of the semester kind of stuff? All right. So let's flip it back. So, L'Hopital. I hadn't really looked at the Muppet one here. Me trying to solve a limit. There's infinity over infinity. There's zero over zero. Ah, what do I do? L'Hopital coming to save the day. So, when we first learned about limits, and we were going to take a limit of this, did we need to do something like the quotient rule with the limit? Or does the limit actually distribute across division? So y'all remember anything like a quotient rule for limits? And we did it for derivatives, but for limits, no, it was just distribute that limit through. So when we're looking at the quotient of two functions, what we're asking is, as we get closer and closer to a particular value, what are these two functions doing? And when we're looking at the quotient, what we're actually looking at is which one grows faster? Do they grow at the same rate, or is one faster than the other? So when looking at those growth rates, like sometimes we plug in the number and we get 0 over 0, or we could get infinity over infinity. Both of those are what we call indeterminate forms. When we get 0 over 0, that doesn't necessarily divide and become 0. It doesn't necessarily mean infinity either. It could mean either of those or something else. So we call it indeterminate because it doesn't tell us anything useful. It doesn't help us determine the answer. So 0 over 0 is an indeterminate form because we can't tell which of the two is growing faster from that information. I can write a function that the limit would be 0 over 0, where the top is going to explode fast, or the bottom explodes fast, or they grow at the same rate and the limit actually ends up equaling a number. So, like this one here, indeterminate form. So if I plug in the 2, I've got 2 squared minus 4 over 2 minus 2. So 4 minus 4 is 0, 2 minus 2 is 0. So direct substitution gives us an indeterminate form. When we were doing limits before, what this meant was, well, you got to go back and try some algebra tricks. So the x squared minus 4 factors into x minus 2 and x plus 2. And so this is an equivalent way to write the function. Within a limit, I can cancel things out. The resulting thing that I'll have left is no longer equivalent to the original function. The original function is x plus 2, but it's got a hole at x equals 2. When I cross these out, now I'm just saying, oh, it's like x plus 2. And it is everywhere except at 2, which is the thing I just canceled out. So the limits are equal even though the functions are not the same. But now that we've canceled out the offending factor, we get that the limit as x approaches 2 of this quotient is 4. So even though we can see in the original formula, when we tried plugging in the number, we got bad math. It's a hole there, but that hole is at 4. Indeterminate form of sine x over x. Sine of 0 is 0. And 0 is 0. So this one, we actually had to solve using squeeze theorem, I think. However we did it, like this became a defined limit that it equals 1. Now, what L'Hopital's rule tells us is if f and g are differentiable functions over an interval containing the value that the limit is going towards, and we get 0 for the top function and 0 for the bottom function, then we can take the derivative of the top on its own, the derivative of the bottom on its own, put them back in a quotient, take the same limit, and they'll be equal to each other. So this holds true if, assuming that the limit on the right actually exists, or is infinity or negative infinity. It also holds true if we're only looking at a one-sided limit, or if we're approaching infinity or negative infinity. So if we get 0 over 0, then we can do our derivative. And the limits will be equal. So looking at this one, we plug in the 2 again. It's the same problem. So we know we're going to get 0 over 0. But now we're going to apply L'Hopital. When I first learned it, I was like, hospital. It looks like hospital. I'm just going to call it hospital. So that's like how it was in my head.
It actually just doesn't.
So this guy's name is like the hospital. Sorry, I shouldn't laugh, but it is named after a French mathematician. So, okay. I feel a little bit better about messing up his name. All right, so x squared minus 4. Now we're not doing the quotient rule. We're considering these as two separate functions. So just on top, x squared minus 4. What's our derivative? So you can still do that, but this is faster and works if it doesn't factor as well, or if it's not obviously factorable. So I take the derivative, that'd be 2x, and then minus 0 over 1 minus 0. So now I have the limit as x approaches 2 of 2x over 1. Now we plug in the number, we get 4. Same answer, but I didn't have to factor. So we first have to check that we got an indeterminate form. Once we see that it's a 0 over 0 or infinity over infinity, then take the derivative of the top, take the derivative of the bottom, two separate things. And now look at that new limit. Whatever that answer is, it's the same as the answer to the first one. 1/0 means either positive or negative infinity. Or like any sort of constant over 0. Well, undefined when we're talking about limits means one of the infinities. It's hard to tell if it's positive or negative without considering like the actual function itself. But when we have something constant over 0, where as we approach 0, we're using really small numbers, but dividing by a small number is the same as multiplying by a really large number. 0 divided by 2. Like, what is 0 divided by 2? 0 divided by 7. Still 0. Yep. So 0 over a number is just 0. But totally normal to have that question because we get so used to 0 being all sorts of crazy, especially once we learn L'Hopital's rule, that sometimes we forget 0 over a number is just 0. Now, what you're going to see on the writing assignment is 2 people were doing a limit. They did it 2 different ways. And at least one of them screwed it up. I didn't actually pay enough attention to see if the other person did as well in a different way. So here, the only reason I remember this is 1 is not because I remember like how it's proved. I remember it by using L'Hopital's rule. So we do our checks. Sine of 0 is 0. So 0 over 0. Indeterminate. I hate that word. So now we can use L'Hopital's rule. All right, now the hard question. What the heck was the derivative of sine? I know the bottom is going to be 1. But where does sine go for its derivative? Yeah, it's cosine. For me, I always had to stop and think, is it positive or negative? It's, for the trig functions, if you're taking the derivative of something with a c, it's negative. If you're taking the derivative of something that doesn't start with a c, it's positive. That was one of the rules I taught myself because my teacher made me memorize all that crap. So like the derivative of cosine is negative sine, but the derivative of sine is cosine. But what you're going to have to sort out in your head is we're also going to talk about after exam 3 antiderivatives. So you have to sort out the difference between derivatives versus antiderivatives go the other way. And now that C rule, yeah. So now when I plug in 0, the cosine of 0 is 1. 1 over 1 is 1. I think that word is going to get shortened to that because that is way too many letters. But it's very easy to forget that you need an indeterminate form to apply L'Hopital's rule and just be like, I'm just going to apply it wherever because it's fun. Yes, I know I have weird definitions of fun. So let's see what happens on this guy. So we do our substitution, negative 11, the natural log of 7 minus 6 over 7 minus 7. So it's a 0 on the bottom. And then we have the natural log of 1. So remember, natural log is undoing an exponential. So this is asking e to what power equals 1. So it's really what number, any number to what power equals 1. If I do 2 to the first, 2 to the first is 2. So it's not the first power. So what power will turn something into a 1? So I know 2 to the 1 is 2. I know 2 to the -1 is 1/2. So 2 to the 0 is supposed to be in between these guys. And if I look, it's like divide by 2, or multiply by 2, multiply by 2. So 1 is the guy in the middle. Like, so 0 power is the thing that answers what's the natural log of 1. Any log of 1 is 0. Yep. So it is indeterminate. So now we got to do derivatives. Well, derivative of the bottom's nice. I'll just skip to the bottom. That'll be 1. Because the constant would be 0, so I'm not even going to write it. Now, how do we do derivatives of natural logs? What does that end up happening? 1 over the thing we're taking the natural log of. So 1 over x minus 6. And then I always at least think about chain rule times the derivative of what we just wrote on the bottom, the inside. So what's the derivative of x minus 6? Yeah. So here the chain rule doesn't give us any useful information, but the like 1 time out of 10, it does. And I find, it doesn't hurt anything to think about it the other 9 out of 10 times. So you don't have to write the times 1 there, but that chain rule thought is a good one to have. So now let's see what happens when we plug in the 7. We get the random number that was multiplied out front. So minus 6 is 1, 1 over 1 is 1, times -11, -11. So it means when we're looking at the natural log of something compared to a linear function, they're growing at the same rate, essentially. Now here's one that's been bastardized a bit. So our limit is as x approaches -2. And if you look on the bottom, -2 plus 2 is 0, squared is still going to be 0. So on the top, especially since we're in the L'Hopital section, it's probably going to be a 0, but we still should check. All right, so e to the -2 plus 2, that'll be e to the 0, which is 1. And then -2 plus 3 will be 1. So the top is 0. And then our bottom, -2 plus 2 squared, 0 squared, absolutely 0. So we do have an indeterminate form. So applying L'Hopital's rule now, we keep our limit the same. Still as x approaches -2. The e to the x plus 2. The derivative of that is, that's our lazy derivative, e to the x plus 2. Times chain rule, derivative of x plus 2 is 1. Minus, what's the derivative of x plus 3? Just 1. Derivative of x is 1, derivative of 3 is a constant, so it goes to 0. And then on the bottom, we can do that one as a chain rule. So I've got ugly squared, so I use my power rule. 2 ugly, ugly being x plus 2, times derivative of the inside, well, it's just 1. All right, so now plug in the -2 and see what happens. We're gonna get e to the 0 again, -1. So we got 0/0 again. Still indeterminate, so we do the derivative again. So on top, e to the x plus 2, derivative of that is e to the x plus 2. The -1 is now just a constant, derivative of that is 0. Down here, 2 times the derivative of x plus 2 is 1. So now when I plug in the -2, we get e to the -2 plus 2 over 2, e to the 0. So we get 1/2. So depending on the function, we can apply L'Hopital's rule more than once to evaluate a limit. And this right here is like picture perfect classic test question. Now, if I incorrectly tried the derivative again, the derivative on the bottom of 2 would be 0. And then I'd have a number over 0, and it's like, whoa, 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 whoa. What? Like anytime if you do L'Hopital's too much and you end up with a constant over 0, like rewind a step, make sure that you could still apply it from the line before. So questions on that one? Questions so far? All right, so now these, we're asking what happens as x approaches infinity? So if we actually graph these three things, they do very different things as we continue to the right. So the top as x goes to infinity, goes to infinity. The bottom also goes to infinity. And in fact, we're going to get that for all three of these. And the way we solved these back in chapter 1 is we would multiply by 1 over x to a power on the top and the bottom. So it like rewrites the way we're looking at the function. So we can focus on the largest power terms. So this first function, since the bottom has an x to the third, the top only has an x squared. As the x values get bigger and bigger, the bottom will grow faster than the top can. So eventually the bottom is getting bigger and bigger and bigger. So it's going to force the fraction to go to 0. Here, when we've got the quotient of two lines, I plug in a number for x, I minus a 1, or I add, multiply, and then those little things. But really, the x's are going to grow at the same rate. When I plug in 1,000,000 there, minusing 1, like multiplying by 3 has a change. Minusing 1, or adding 5, not so much. So really, this limit ends up approaching the coefficients there. And if you graph that, it actually has a horizontal asymptote of 3/2. If you graph this first one, it has a horizontal asymptote of 0. It approaches the x-axis as we move further and further out to the right or the left. This third one, though, the top is growing bigger. So this one is going to approach infinity. So we got the same indeterminate form, but the answers, the solutions to the limits are vastly different. The good news is L'Hopital can absolutely handle this for us. So if you look at the guy in the middle here, if I take the derivative of the top, I get 3. I take the derivative of the bottom, I get 2. Oh, look, that's what the limit was. You know, if I took several derivatives of the top versus the bottom, because anytime there's still an x, your limit's still going to be infinity. So this is why people will sometimes over-apply L'Hopital's rule, because when you're looking at the infinity over infinity case, you do end up using it quite a bit. So I'd have like 6x plus 2, and then that would become 6. If I do 2 derivatives down here, I'll still have an x. So I've got 6 over infinity. Yeah, it goes to 0. Whereas here, after one application of L'Hopital's, I still have an x on top. The bottom would be a constant, so it's going to go to infinity. The top grows faster. So this is just the ridiculous formal definition for using L'Hopital's rule for the infinity over infinity case. Now, it is possible we don't have to be approaching infinity to get an infinity over infinity case. Like there's some functions that have vertical asymptotes. As we approach those x values, we can get an infinity or a negative infinity. The mom look has power. Oh, well, if I'd known it was here, I wouldn't have talked about it. So here is literally the middle example from up above. But now when I use, I check, I plug in my infinity, yes, it's going to be infinity over infinity. So now I can apply L'Hopital. And we just get a constant, so that is what the limit equals. All right, here's our next ridiculous miss. So this is L'Hopital's to the ridiculous. Absolutely would not ask this on a test, but it's kind of cute to do as an example. So e to the t, exponential functions. We know the derivative of that is e to the t. So the rate of change is the same as the original function. So no matter how many times I take the derivative, I keep getting the same thing back. So there's a lot of ways we exploit that in math, but for something like this, when you're comparing e to the t versus any sort of polynomial, e to the t always wins. You might have to get to really big values, but that exponential function will eventually grow faster than any polynomial. That's what we're gonna see with applying L'Hopital's rule here. So infinity plus infinity over infinity minus infinity, it's still infinite. So the limit is t approaches infinity. Now we'll have 9t to the 8th, and down on the bottom, 8t to the 7th. And then we get another infinity over infinity. I'm not going to write all of these, but I do just want to write the first two so we can kind of see the pattern that's being established. And again, we get another infinity over infinity. So if I was going to write the next derivative, what would I put in front of, like I'd have e to the t plus, what would I write next? So what's our derivative of t to the 7th? Yep, bring down the 7, t, take 1 off, so it'll be t to the 6th. So I have 9 times 8 times 7. And then if I do the next derivative, it'll be 9 times 8 times 7 times 6. So I'm gonna several later insert SpongeBob meme here. So on the bottom, eventually, we're gonna get e to the t minus 8 times 7 times 6, blah, 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 all the way down to times 1. And on the top, that will be 9 times 8 times blah, 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 all the way down to 2. And that'll be t to the 1st. And still with the e to the t plus on there. So it's still, because it's e to the t over e to the t, it's still infinity over infinity. But the derivative of the polynomial term on the bottom goes away one derivative before it does on top. So like the next step, we're going to have e to the t plus the shorthand notation for writing a descending product like that is a factorial symbol. Because in certain forms of math, you end up writing that repeated descending product way too much, so. Still infinity over infinity, though. We do L'Hopital's one more time. And we get e to the t over e to the t. Well, what is an ugly thing divided by itself? Which one? Why one? Whenever I'm not sure, I go back to like basic numbers. So 3 divided by 3. Oh yeah, that's 1. 7 divided by 7. Yeah, that's 1. Okay, yeah, it's 1. Yep. To most mathematicians, though, this is like cute and adorable. Like, oh, look, we got 1. And it's like cute and adorable to look at. It's not cute and adorable to think through. It's certainly not cute and adorable to write out the derivative every step of the way. But even something that grows as ridiculously fast as something raised to the 9th power, e to that number is still eventually going to be bigger always. All right, so 0 over 0 and infinity over infinity are like our best friends. Those guys we can straight up use L'Hopital right then. These other guys, we've got to mess around with it. So if I get 0 times infinity, then I have to take one of the two pieces and flip it to the bottom of the fraction. If I get infinity minus infinity, then here we're typically looking at a fraction minus a fraction. So your algebra step is then combine the fractions, then figure out where you go. So when you get these guys, it's do some algebra to get 0 over 0 or infinity over infinity. These guys, though, to make them do, you end up using a log. And it gets a little weird, but basically, a lot of the things that I can do to both sides of an equation, I can do to the inside and the outside of a log. So we'll see some of those. We didn't put one of those on the test. They're good practice. It is a good, like, math knowledge to have, but it is kind of a weird fringe case. All right, I think it actually moves into other indeterminate forms. I'm gonna leave that for Friday because we have 4 minutes left, so I think that's a good stopping point. All right, so practice problems should come up tonight. Take a look at those. Take a look at the writing assignment because we'll probably move through the rest of this pretty quick, so we might have some extra time on Friday. You could ask me about the writing assignment or the practice problems. So just keep an eye out for that. All right, let me stop the recording.